Good afternoon. It's my pleasure to present the speaker today, Professor Anton Andronic. He is a professor at the University of Münster in Germany since 2018, right? Before, he was a staff scientist for maybe 20 years in GSI, also Germany, a very important and famous laboratory in nuclear physics and high energy physics. And originally he's from Bucharest, where he got his PhD. And Anton is very very well known in the community for his experimental work. He's let's start. He's project leader of detector in ALICE and also in CBM that he will present today. Is an experiment in GSI. He's also the physics coordinator of CBM currently, and he had many other responsibilities in the past. And besides his experimental work, he's also very well known by his work in statistical models in heavy ion collisions. He has even a very well-known Nature article about that. So it's really a privilege to have him here. And actually, also important information, he's also advisor or co-advisor of 2 PhD students from our university. We have this co-tutel program with the University of Münster. So Lucas is one of them, and Leonardo is not here yet. But there is 2 PhD students that are co-advised by Anton. So it's a very nice program between the 2 universities. So we have a very close connection with him, and that's why it's such a big honor and pleasure to receive him for this colloquium. He's also actually giving a course. Who is interested? We had the first class today, but there are 3 more. So if anyone is interested in his course, it's between 10 and 12 every morning until Tuesday. And we'll be here actually tomorrow, Monday and Tuesday, we'll be here, the class. So if you are interested, students around are interested, please come. You don't need to register, just come and watch his nice classes. So Anton, thank you very much, and the floor is yours.
Thank you, Marcelo. Thank you for the invitation to give this colloquium. It's a great pleasure and honor to be here. I have chosen as a subject our mainstream activities in ALICE, where also Marcelo and his group is active, and I will say something about the CBM and the future detectors briefly at the end. So I focus more on the study of hot and dense quark-gluon matter at the LHC, and the future facilities will be mentioned briefly, as I said in the outlook. I have here a menu. I will start slowly with reminders of things you all know, but I thought I should start from the very basics and introduce the experiments as well, and say a bit more about our own experiment, ALICE. And then my main focus will be about the studies of the phase diagram with light flavor, light quark, hadrons, up-down strange, and then I will say show some results and present a picture of jet quenching, a little bit of heavy quarks and deconfined matter. And I have here not included explicitly, but I will address also a dynamical picture of the model, not only a statistical one, and then summarize and give an outlook. You all know this. At the deepest scale, matter is formed out of quarks and gluons, while quarks are the matter particle and the gluons those mediating the strong interaction that builds from up and down quarks, protons and neutrons that are the constituents of the nuclei, which in turn carry the largest mass, the largest fraction of the mass in the normal ordinary matter. Protons and neutrons are baryons, the pion is a meson, and there are of course many more species, and there are of course more species than these classical standard ones, 4 and 5 quark species, some of them exotic. Still hotly debated. Some of you play a role in that debate. What is depicted here is actually very schematic. What is true here is only in concept true. The scales are not like this. The quarks are not of this size compared to the size of the protons. The colors that we have here as charges for the quarks are not real colors, of course. They are abstract quantum numbers coming in three types, and then anticolors as well on top. So these are the peculiarities of the strong interaction. And a special property is that those colors and the quarks that you see here are never found free, isolated, so to say. So they are forever bound in hadrons like the baryons and the mesons and other species. The up and down quarks is only the first family. There are two more families of heavier quarks, and there is the mirror family of the leptons, not a mirror, but the corresponding family of the leptons, and then the force-carrying particles and the Higgs boson are depicted here in this Mendeleev table of elementary particles. So the deepest level of our knowledge of the structure of matter. Now the proton, if we look at it with enough resolution, may look like this. This may be a snapshot of a state of a proton where the three valence quarks, the two up and one down, are supplemented by virtual pairs of quarks and antiquarks and by many gluons carrying the interaction. So the way this looks is depending on the resolution. And this is a look at the proton with a resolution which is much better than the one giving us the static proton that you have seen in the picture before. We know the charge radius of the proton. There is a bit of controversy about that too. We don't know fully how the spin of 1/2 comes about. We know roughly, but not completely. And once again, I repeat here, the quarks are never found free, and this is a quark confinement principle. That means a mystery of the nature. It's made the principle because that's how nature seems to work, but this is something that we don't really understand at a fundamental level. That the proton is not just seen here is not an abstract theoretical picture, but a real one that is being seen in experiments. Actually, such a picture is derived from measurement and not from theoretical considerations. We observe also directly in collisions of protons at the LHC. This is a snapshot and picture of how two protons lead in a collision to several tracks in our detector. And if we do sample 1 million more collisions, sometimes find such pictures. Rarely, but a case where a busy proton collided with another busy proton and many scatterings happened and many more particles are the outcome of that collision. The theory of strong interaction, QCD, quantum chromodynamics, is characterized in addition by the varying strengths as a function of the intensity of the collision, which is the momentum transferred in such a scattering process. That is also very special. This strong variation and the decrease in particular is unique to the strong interaction. All the other interactions, electromagnetism in particular, do not have these properties. There is some varying strengths, but it is at the different scales. It's completely different. So at large momentum transfers, large energies of the collisions, roughly speaking, the strength of the interaction is small, and perturbative methods can be used when calculating processes. Conversely, at low momentum transfers here, the strength of the collision does not allow for real, explicit or for rigorous calculations. One needs models. One needs to model the physics such that one would be able to calculate. And that's being done in this regime here of the deconfinement. We have the theory now taken with all its ingredients and put to work in a numerical way. And this numerical way is per se quite sophisticated. Gives us, as a function of the temperature of a system, so now we have a pot of quarks and gluons, and heat it in a static way, And this is the axis here of the varying of the temperature for a system of quarks and gluons. And this is a rigorous calculation, but in a numerical way, so to say. But it's not an approximation. That's an important thing. What exactly is behind it is a sophisticated thing. I'm not an expert, and I cannot speak very long about it, but you have to believe me, as I do believe my colleagues who do this, that this is a rigorous way of doing strong force calculations as a function of temperature for a system of quarks and gluons. What is plotted here is the energy density and the entropy density, so basic thermodynamical quantities normalized by powers of temperature. So if nothing happens, so in a system that evolves continuously normally, these quantities, so without new degrees of freedom, just same, when nothing happens, these lines should be horizontal, purely horizontal. Because they are normalized already. Of course, the energy density and the entropy density increase strongly with the temperature, but the normalization is taking care of this. So if things are boring, it will be a flat line, horizontal line. And you see here that we are far from this boring situation. At low temperatures, we have low values of the energy density, and as temperature increases here, we get to considerably larger values. Note that we start the axis here at about 100 MeV in temperature. In real worlds, in real units, temperature, this temperature is 10 to the 12 Kelvin. So these are crazily different values compared to normal life, so to say, or to normal lab temperatures. So this is really an exotic matter, and at this level, at low temperatures in this plot, we can explain the values by just considering 3 pions, pi plus, pi minus, pi 0, the very basic hadrons that one can build. And one ends up with a value which is closer to unity. So you see, this is what we get here. Rather easy. At higher temperature, we can approximate the system with a gas, non-interacting gas of quarks and gluons, and again, in that limit, we can calculate. And I quote the values here, and you see that these are the arrows that are shown in this figure. So we approach this limit of an ideal gas of quarks and gluons, but don't really reach it. So we still have interacting quarks and gluons, but what we see here is that from lower to higher temperature, there is an onset of degrees of freedom, and this is the onset of degrees of freedom of quarks and gluons, at variance to the case of hadronic degrees of freedom at lower temperature. So this is the theoretical basis for investigating compressed and heated quark-gluon matter also in laboratory to see whether these predictions are realized in reality, so to say, in the lab. I have a brief interlude about the units. We use natural units where h bar equals c equal 1. And this is why in the previous plot, these quantities normalized to the temperature were without units. And we use, in addition, the Boltzmann constant equal 1. So this is a bit of a strange system of units, but it exists. One can use it. It makes life easier. That's all I wanted you to get from this. And this is why, actually, because of the Boltzmann constant, that the units of energy is in units of temperature to the power of 4. This state of matter of quarks and gluons must have existed in the early universe the way we understand it within the standard model of the Big Bang. You see here the evolution of the universe in time and in size, schematic, of course, and we see sketched a few stages from today to the time of the formation of the galaxies, to the time of the release of the cosmic microwave background, to the time of the nucleosynthesis, which led to the formation of deuteron and helium-4 nuclei, mainly, to the time, about 10 microseconds, here noted by this yellow arrow, where out of a gas of quarks and gluons, hadrons like protons, neutrons, pions have been formed. So earlier, there could have been an electroweak phase transition, there must have been, But the last moment in the history of the universe where we have direct observations, measurements, is this one about 100 seconds after the Big Bang, where nucleosynthesis took part. Namely, formation out of protons and neutrons of deuterons and helium-4, dominantly. A little bit more, but not so much more. About this stage where quarks and gluons transformed into hadrons, what we call hadrosynthesis, we don't have an access experimentally in what concerns the history of the universe. So you see the drive, the necessity to produce such a state of matter in the laboratory and characterize it in measurements in the lab. To do this in the laboratory, we cannot cook quarks and gluons in a pot. We are forced to do it in a very dynamical way, namely by colliding nuclei against each other at higher energies. Now, we produce compressed and hot matter, dense and hot, and by necessity, it will have to expand and cool in the vacuum. So that is also unavoidable, and the only question is whether we are able to catch properly the remnants and be able to characterize from the remnants that we measure at the end stage of such a collision, characterize the state of matter produced in an earlier stage in this hot and dense stage. So what is shown here are snapshots of the different stages of the collision. Initial, overlap, hot and dense, expanding inward farther and cooling, and then flying away, the remnants, the particles flying away undisturbed to our detectors. So we measure at this stage and need to run the movie backwards to determine the properties of the matter at an earlier stage. And please note that the total duration of the movie is about 10 to the minus 23 seconds. So it's something that is not an easy way to record and then also to run backwards. And the total extension of this fireball, hot and dense, at the end mostly is of the order of 10 to the minus 40 cubic meters. So it's extremely, crazily small. No way to put it under a microscope. So we have to do different methods than the ones we are used to in normal labs in investigating the properties of matter in solid state physics, for instance. I have sketched here the different phases. I will not discuss them, but only in details. Only I would like to point out that I will address mostly this phase where the hadronization takes place, namely the conversions from quarks and gluons into hadrons, and that is the stage of the, in the sketch before, of the early universe at its age of about 10 to 20 microseconds, at most 100, but in this 10 to 20. And then I will show something about how we run the movie backwards or forwards and via dynamical models and try to how to make the connection with the experiment and extract relevant physical quantities. I will focus mostly on collisions in the Large Hadron Collider, sketched here in the chain of the accelerators at CERN. In 4 stages, the nuclei as the protons are accelerated here. The 3rd stage and the 4th is the Large Hadron Collider. You have seen it sketched in the landscape around Geneva. Here is the Geneva airport, so it's really a huge machine, 27 kilometers circumference, as you already know, definitely. Inside the ring, there is a complicated, complex structure of magnets of different types to keep the beam. Of course, there are radio frequency cavities to accelerate the beams, and then the magnets to keep them on the trajectory and focused. Those deflecting the beams in the circle are those in blue here, the dipole magnets, and there are some quadrupole magnets for focusing and higher orders as well. A proton beam circles this ring of almost 27 kilometers, about 11,000 times per second. The temperature inside these blue vessels is just 2 Kelvin. In such a big volume, this is the coldest place on Earth in this sense. This is the machine that led to the production and detection of the Higgs particle by our colleagues in the ALICE and CBM experiment. My own experiment was not able to see this, but fortunately they were designed for this, of course. And in 2012, the big discovery was announced and led to the Nobel Prize for Higgs and Angler a year later. These are the 4 LHC experiments: CMS, ATLAS, LHCb, and ALICE. They are not equally big, but comparably big, and comparably complex in their own way. Each, in fact, has its own personality. I would not be able to describe this. I will focus a bit on my own experiment, which I, of course, also know best. These are also very big collaborations, I must add. 40, 50 countries, of the order of 200 institutes, and of the order of 2,000 to 3,000 people, even beyond 3,000 in ATLAS and CMS by now. The beams, the 2 beams in the collider come from the left and the right side and meet here in the center of the detector. That's true for all the experiments conceptually. And the remnants of the collisions are detected in several layers of detectors, all of them in magnetic fields of different geometries, to measure the curvature of particles, to extract momenta, to measure signals, to extract particle identities. So that's the conceptual way of doing such a measurement. I'll say a few words in a minute. What are the control parameters? When we collide these 2 nuclei, what can we vary? We can vary the energy of the collision. Here I will focus mostly on the LHC. I will not do much variation, but a little, one aspect. And then we can vary the displacement between the 2 nuclei, namely what we call the centrality of the collision. Central collisions with full overlap, mid-central or peripheral collisions when the overlap is smaller. So like this, we vary the volume of this hot and dense matter component fireball that we want to investigate. So these are the control parameters. I want to add that that varying the centrality, the displacement between the 2 nuclei, is not possible in a controlled way in the experiment at the moment of the collision. We don't have the precision, the required precision, which is a few Fermi, to displace the beam or to control the beam. So we do all possible geometries and sort out the different collision classes post-mortem, offline, so to say, after the collision took place, from signals in the detector. So that's the procedure. And we have a good control on this, and these are central collisions here and less central in this direction. So that's all to convince you that we keep things under control despite not being able to control the beams in that precision required for the collision. So we measure transverse momentum of particles emitted with respect to the beam axis, transverse to the beam axis. We measure angles, also longitudinally. Rapidity is more or less a velocity in the longitudinal direction, but reconverted such that it is additive to Lorentz transformations. And for instance, we count particles as a function of rapidity. So in the longitudinal direction, how they are distributed, and we count them, and you see that we end up to more than 2,000 per unit here. And if we integrate all of this, we end up with about 30,000 particles for a central collision. So we collided 2 nuclei, each with 200 nucleons, so in total 400 nucleons, and end up with 30,000 particles. So you can realize there was something going on, right? And so this is there is a strong effect of the interaction of the hot and dense fireball produced there that led to so many particles. And these particles not only are produced in large numbers, they also go away with large velocities, collective velocities of the order of 60% speed of light. So a lot of energy is transferred in the collision from the beam into the hot and dense fireball, which we detect at the end by counting particles in this simple example here. The shape is a bit boring because it's a Gauss, but the numbers are what is the important part here. So in these collisions, we usually take many of them, like our colleagues in particle physics needed many collisions to detect the Higgs boson. We also need many collisions to be able to classify in different groups and have enough precision in studying the processes. So we take by now many billions, tens of billions of collisions have been accumulated until now. So it's a huge number. We usually measure charged particles because they are operationally, technically easier to do, but we do measure neutral particles as well. So it's not exclusively, but mostly charged particles. So we count, we measure momentum and or velocity, we identify particles. So the complexity of the detector is used to be able to perform such measurements. And then we also measure the correlations between particles. So we don't measure them one by one, but all at the same time. So we have all the correlations and we can do correlation studies. The detector acceptances is restricted in a phase space. You cannot measure all the angles. You have to have a slice of the distribution of the particles. This is a technical limitation. And the single particle detection efficiency is of the order of 80%. So we don't have perfect detectors. We miss some of the particles, 10, 20% of them. And this we have to correct by modeling our detector in a special Monte Carlo procedure. That's per se. It's quite laborious and requires a lot of work. So what I'm presenting here is essentially a tip of the iceberg, really a simplified picture of what's going on when we do such measurements. This is a pictorial summary of collisions at the LHC. Proton-proton collisions, proton-lead, xenon-xenon, lead-lead in the so-called run 1 and 2 up until 2018. From 2022, we started run 3, which we will be finishing in by middle of next year. And here we had a bit of higher energies, and then recently oxygen-oxygen and neon-neon collisions. And the so-called heavy ion run is about a month's collision time per year. The rest of about 8 months or so is devoted to proton-proton collisions. Recently, actually, in the stop between 2 runs, the ALICE experiment and others, not only ALICE, but ALICE in particular, was upgraded. And for the time projection chamber shown here, a detector of 5-meter diameter, you see a picture of the brave people who, under COVID situations, did the upgrade. Actually, there was a very important Brazilian contribution. The ESP had a significant contribution and was leading the development of the so-called SAMPA chip. It's hidden here. You cannot see it. It's hidden here behind the cooling pipes and the connectors in this part, this end cap of a cylindrical detector. This is a cylinder, and what you see here is just the end cap of the readout chambers and the electronics with their infrastructure. A more zoomed in picture inside the TPC, the time projection chamber. So in this hole, we installed silicon pixel detectors of a new technology, and they are shown here with these yellow layers. This is the beam pipe, and the yellow layers need to be as close as possible to the beam pipe in order to do measurements of the needed precision. So a complete picture looks like this. Again, a diameter of 5 meters is this cylinder here, length of about 5 meters too. In a central collision, in this case, recorded are about 3,200 particles, primary particles. There are some secondaries as well, which are cleaned out. And the camera is the time projection chamber and the tracking system. All in all, with about 13 billion pixels. And we take up to 50,000 pictures per second. So this is a 3D camera of this performance. And we do a continuous readout of 3.5 terabyte per second in normal mode. Then this is all reduced then later on. This is not what we save on disk, but the initial input rate of data at the detector is 3.5 terabyte. And then it's, as I said, reduced in several steps on a computing farm. So this is the craziness of picture taking, so to say. And from this on, physics starts. And physics starts by identifying particle. I will not explain how, just show you this picture where you see the identity of the particles. Pions, electrons, kaons, protons, deuterons, triton, helium-3. And to obtain such a nice image of the identity of the particle, again, there is a lot behind and a lot of struggle and a lot of computing and detector finesses. whenever there is an overlap and uncertainty in the precision, in the particle identity, we use other detectors. This is from a single detector. That's why we need several detector types in order to combine and get a clear identity of the particle. And this then brings me to the first physics result, finally. What is shown here is the measured yield, so the number of particles of a given type per event in a central collision. So you see that per event we have about 1,000 pi plus and pi minus each, almost. And helium-4 nuclei, the heaviest particles in this plot, are produced 1 in a million collisions. So you see here the need to measure many collisions in order to get to measure rare particles as well. The measurements are the red points, and the blue line is what the statistical hadronization model gives for the best fit of the data by adjusting 3 parameters. This is a temperature, which comes out to be 156 MeV with an error of about 2 MeV, a baryochemical potential of almost 0, and the volume of about 4,000 cubic Fermi. Again, it's a slice of the total distribution of particles in phase space, not the whole volume, but a slice in the middle, somehow in the middle. What you see that the agreement between data and model is very good, as you see in the ratio down below here. And this shows us that chemical equilibration, so the thermalization in the sense of particle identities, has been achieved. This is a model that assumes chemical equilibration, and the model explains the data. That means we have a very good proof, via a model of course, but a very good proof that chemical equilibration has been achieved at the moment where we measure the hadrons, at a later stage, obviously, not at the earlier stage of quarks and gluons, but at a later stage. You see as well that matter and antimatter is produced in equal amounts at the LHC, as far as we can tell. So within our precision of the measurement, you see equal amounts of matter, proton, antiproton, lambda, anti-lambda particles, and so on. So this is a realization in the laboratory of that state of matter of the early universe, 10 microseconds in its lifetime, at a temperature of the order of 10 to the 12 Kelvin. 1.5, 10 to the 12, to be more precise, because we do have quite some precision here. To do this, I write here the formula for the particle densities. We use Fermi, Dirac, and Bose-Einstein statistics for plus and minus here. We ensure quantum number conservation, so this is a statistical model which takes into account the quantum properties of the particles. There is the spin degeneracy here playing a role, and what is shown here is actually a replotting of the previous results as a function of mass. So from simple Boltzmann consideration, you forget all the details and just consider production in ideal Boltzmann gas, you will get in this logarithmic scale a term proportional to the temperature and a minus mass over T, and that means the inverse of this slope is actually the temperature. It's a very simple way to extract, of course, simplifying a bit the details. But this is what comes out. Deuteron is a bound state of protons and neutrons with a binding energy of about 2.2 MeV. And it's still produced, according to this model, at a temperature of 156 MeV. That's per se quite an astonishing thing. And we still keep debating, actually, why can this happen? But it can happen, presumably or likely, because the expansion and cooling is so fast that as soon as you produce the deuteron, you have no chance to destroy it, to melt it again. There is no chance of a second collision, so to say. In the early universe, this was totally different. The universe was cooking for a longer time, and the deuterons were produced over many seconds. And here, our scale is 10 to the minus 23. So similarities to the early universe are there, but not ad literam, so to say. Now, I have done this at the energy of the LHC. And this is now the result. The following result is the one where I vary the energy of the collision. It's not something I do myself, but this is what the community did over the past about 30 years or so. Actually, starting from the lower energy, and this corresponds in this plot on the right part of the axis. Temperature is on the vertical axis, and the horizontal axis is the baryochemical potential. This quantifies the asymmetry between baryons and antibaryons. At the LHC, we produce baryons and antibaryons in equilibrium, in chemical equilibrium. That means the baryochemical potential is 0, very close to. And this is the point you see here. At lower collision energies, matter is dominated by baryons, namely the collision of the two nuclei lead to an overlap of the two nuclei. At the LHC, they go through, and in between is only a field of gluons, is pure energy in a sense that would lead to matter. At lower energies, the two nuclei interpenetrate and cook together, and you have an excess of baryons compared to antibaryons. The baryons of the two colliding nuclei, the protons and nucleons. As a consequence, mu b is large at lower energies in this part of the diagram, and temperature is small compared to the LHC. And if we increase the collision energy in this direction, you see an increase of the temperature and then a saturation. And this saturation corresponds to what the theory of the strong interaction tells us for a soup of quarks and gluons transforming back into the hadrons, and these are the lines shown here in this plot. So from a single point, of course, at the LHC, we may not be able to conclude that the hadrons come from a hot and dense earlier stage of quarks and gluons, but from putting together all these points from the different collision energies from the different particle species, we can conclude that this saturation, this limiting temperature, is what corresponds to the temperature of the transition from quarks and gluons to hadronic matter. We do have measures of temperature via different methods, and I would like to just describe one more. What I've shown before is this snapshot at the transformation of the quarks and gluons into hadrons. This is the chemical freeze-out temperature and the demonstration of the chemical equilibrium between those particles via the comparison to the model. Via a model called hydrodynamics, well, hydrodynamics is not a model, it's a general theory, but applied to our field, we could determine a range of temperature. This range of temperature is what I was meaning by running the moving backwards. So we start the calculations at a given momentum with a given temperature or energy density and let the system evolve down to a lower temperature and building of a collective flow together at an earlier stage. And from these measurements, we can then probe this range of temperature. This we do by exploiting the fact that we have a symmetry plane where the two nuclei collide. They define a symmetry plane. And the overlap region they built in the collision has this asymmetric form, this rugby ball type. And you see intuitively from this form that the gradients of energy density or of pressure are stronger in the horizontal direction in this plot than in the vertical direction, just by the way it is constructed, so to say. And this should lead to a preferential emission of particles in the horizontal direction, which is the reaction plane defined by the two nuclei colliding, than outside of the reaction plane. Schematically shown here in the isotropic case, or in the case where the emission would be preferentially on the horizontal direction, would lead to a Fourier coefficient in the azimuthal expansion of particle distribution here around the reaction plane, taking as reference the reaction plane, would lead to this V2 coefficient, which will be positive. That's the expectation. So if it goes with pressure gradients and expansion out of a compressed zone, we should see a positive V2, and it should have a certain magnitude, which one can compare to a theoretical model. This is schematically something more quantitative, the overlap region, the rugby ball in terms of the energy density. These are the color-coded regions here. And after the expansion, after about 10 Fermi over C, in the evolution of the system, you see preferential expansion in the horizontal axis, but it's not a pure quadrupolar expansion. It has also components of octopolar form, this triangular shape, which is sort of folded in here. Not easy to see geometrically, but part of it. And these are the fields of the velocity in this expansion. So if we plot this V2 that quantifies the coefficient in the Fourier expansion that quantifies this asymmetric expansion, we see as a function of the number of particles in a collision, the points are the measurements and the lines are the hydrodynamical description of the measurement. And you see that the hydrodynamical description is very good both for the V2 as well, which is the quadrupolar component, as well as with for the octopolar component as well. So this shows that the system evolves in local thermal equilibrium over long times in this expansion and cooling phase. There are many finesses in this, and experts are partially in the audience, but this is the basic observation at the LHC. What we put in the model here is an equation of state, namely a relation between the energy density and the pressure, which is derived from the basic theory, as I was explaining before, the one that gave us the transition from hadrons to quarks and gluons in this regime here. And this microscopic description of the matter in terms of hadrons in this part and of quarks and gluons in this part, and the transition between them is what is the essential ingredient in the hydrodynamical model to explain the experimental data. I will skip the rest, only show you that in terms of a viscosity, shear viscosity to entropy density, as a function of temperature normalized by the temperature of the phase transition, the critical temperature or pseudo-critical, shows some universality. If you plot this for water, you see the blue curves here. For helium are the green curves, and for quark-gluon plasma, for the matter of quarks and gluons, is the orange curve. And although these TC values used for normalization here are hugely different, 650 Kelvin for water, 4 Kelvin for helium, and 10 to the 12 Kelvin for the quark-gluon matter, in terms of these normalized quantities, the dependencies are rather similar, and in terms of the normalized shear viscosity to entropy density, the values are also not so different. They are not identical either. This is a logarithmic scale, but still they are in the same plot, so to say, right, in reasonable range. Although both viscosity, shear viscosity, and entropy density are hugely different between this matter. So this interesting universality, as well as the existence of a possible minimum around here, around 0.1, is actually theoretically debated in the community, and in order to be able to decode the message behind these observations. Do I have another 5 minutes or so? You still resist for the last 5 minutes? I skip the rest, and in case there are questions, I can come back to some of these results I have included here. I wanted to just say that we measure much more than what I was able to explain to you in this seminar. We measure the sizes to Bose-Einstein correlations between two identical bosons like pions. We measure the shapes of the nuclei through collective flow and hydrodynamics. We measure the alignment of spin of the fireball, which rotates apparently in the semi-central, in this non-central collisions. Angular momentum is imparted on the overlap region, and the alignment of particles with the angular momentum is measurable and has been measured with quite some good precision. The effect of the initial transitory magnetic field is also expected to be visible, but for the moment we aren't able to see it. we impose only limit of what the initial magnetic field, which again is a very transitory, is very short-lived, imparts on particles with spin. Then we are able to turn lead in the collision process to gold, and this is alchemy, and you can imagine that it's actually this byproduct of our collisions that catches the attention of the media, and this alchemy got recently quite well cited in the media. Here is a headline from the Nature, from a Nature magazine. We measure the quantum interference of two raw mesons when the two nuclei collide peripherally without touching each other, without overlap. So it's photoproduction, more or less. And we measure the effective hadron-hadron interaction potential via correlations of this type, although in a bit of a different way, by folding a wave function with a potential. So in summary, I try to convey to you the complexity of our research field and the fact that we break this complexity into different components and tackle them independently and then make the global picture then together, put the facts together for a global picture. I think I have demonstrated that chemical equilibration is achieved. We measure hadrons as final products, but we believe via the limiting temperature and via comparison to hydrodynamical model that they originate from a hotter and denser stage of quarks and gluons, which we doesn't leave enough to be seen in a more direct way, so to say. I have not tackled this, but not only hadrons made of up-down strange, but those made of charm quarks seem to suggest equilibration, and charm quark is much heavier than the temperature we are discussing. Up and down strange quarks have masses of a few MeV up to about 90, 100 MeV is the strange quark mass, comparable to the temperature of 156 then. The charm quark has a mass of about 1.2 GeV, so about 10 times larger than the temperature. And if that large mass quark equilibrates, that's an extra piece of information we obtain about the state of the system. We see strong collective flow, which is well described by hydrodynamics, and this implies an early effective thermalization, which remains not fully understood. That is something our colleagues keep debating, how the early thermalization could so efficiently be realized in just a fraction of a Fermi over C. And we see a strong jet quenching, namely, when a particle with high momentum is produced in the collision, it traverses this medium, which is hot and dense and expanding and cooling, and while traversing it, probes it as well. So this is like doing a Röntgen picture, an X-ray picture with self-generated beams of not X-rays, but of hadrons, of quarks and gluons. That's again, on its own, quite complex, but a very good handle for the properties of the system. What lies ahead for the next about 15 years is keep going and do the ultimate precision characterization of this matter. We are about middle way, so to say. We've seen a lot and quantified a lot. There's some open questions and some precision to be added to this. In fact, all LHC detector will have major upgrades. Actually, there will be more major for ATLAS and CMS in the next long shutdown, and ALICE and LHCb will follow after that. All with rather challenging and wonderful technology, detector technologies. An example I have here for the ALICE the next vertex detector of the ALICE detector, which will employ, you don't see this here very well, but what this shows is a real-life realization of silicon pixel detector with curved sensors, not with individual planar sensors arranged after the other, but by curving the whole wafer, or a good part of it, into a perfect cylindrical geometry, and that is what you see here. After 2030, so from about 2035, in 10 years from now, a new detector called ALICE 3 will be installed, and its magnet is also a technological marvel and will hopefully be realized in Brazil in collaboration, which is just now under planning and, of course, challenging per se. Then there will be measurements concomitantly at the new accelerator called FAIR in Darmstadt with the CBM experiment, and this will explore the region of the phase diagram of the lower energy where the high baryochemical potential points will need a better precision, and also the question whether there is a critical point and a first order phase transition, because at the higher energies of the LHC, the transition from quarks and gluons to hadrons is a crossover. There is no latent heat, no jump of thermodynamical quantities. It's a crossover. It's a smooth crossover. But it could be of first or maybe second order in the region of the low baryochemical potential. The accelerator in Darmstadt is seen here in an aerial picture. Actually, the accelerator itself, the ring here, is hidden behind this picture. But the campus, the place of the accelerator is here. The ring is having this size here. And one of the beamlines right here, you see the completed real-life picture of the cave underground where the CBM detector shown here in a design representation will be constructed right here in this place. The mission of the detector, as I was saying, will be to determine the properties of compressed and hot matter in this regime of the phase diagram, determine the equation of state, determine flow and vorticity, look at criticality, whether there is a first order phase transition or not, then measure the temperature with dileptons to check the emissivity of the fireball, and also measure charm and hypernuclei. This type of matter where baryons dominate, so to say, is a state of matter which may be existing in the center of neutron stars. We don't know exactly. This is still debated. What's the state of matter in this very compressed inner part of a neutron star? And pinning down in the laboratory the properties of this matter would help us understand neutron stars on one side, but maybe better even collisions of neutron stars. When the two collide, the density and temperatures could be similar to what we achieve in the lab in such nuclear collisions. With this, I thank you for your attention and will be happy to answer questions.
Thank you very much, Anton. So now we'll go for questions. Any question? Yeah.
Hi, Anton. Thanks for the presentation, really nice. And can you go back to the slide where you showed the anisotropic flow for different systems that I...
Here.
Yes. So the question is, what is happening with proton-proton? Because
yes,
of course, you can describe the large system, but...
Yes, this is a very good question which is bothering us now since some years. What you see here, the lead-lead collisions are the black points and line, xenon-xenon are the red points and line, and then the blue points are the proton-lead collisions, and the orange points are proton-proton collision. So you see that when you collide smaller systems, proton-lead, proton-proton, for the same number of particles emitted in the final state, you get similar but not identical values of the flow coefficients. In the n equal 3, that's almost identical. In n equal 2 is actually different because the geometry of the collision is very different. So that's the first thing to note here. And then you note that the models explain proton-lead, the hydrodynamical model explains proton-lead quite well, but does not explain proton-proton at all. Proton-proton is, in fact, such a small system that it's very difficult to imagine an early thermalization that would then lead to collective flow. But since we do measure these values here, that seems to be the case. So we probably have to throw out the prejudice somehow and see what one would need in the models in order to explain this data. because there is nothing wrong with the data. I mean, we debate a lot, and we don't really have an alternative explanation that really flow. It's starting for a much smaller droplet of quark-gluon plasma, but it's much denser in this regime of high number of particles.
I see.
So this is the ongoing debate. We don't really have an explanation of this, but the community is working on to deliver. Yeah.
Yeah, but there are any like new strategies to try to understand this better, like because now we publish the.
Yes, we have
right?
oxygen, we have neon. What the new data show is that the geometry of the collision is essential to explain in the magnitude this Fourier coefficients. And, but this does not really shed a new light on the proton-proton collision. So I think we have to keep going and look at higher order coefficients and maybe try to look at event shapes which can be engineered somehow in a symmetry and so on. I don't have a clear strategy myself. If I would have had it, I would have been luckier, but no.
All right, thanks.
Thank you.
More questions? I think Fernando.
I just try to understand a little bit the landscape of possible phases that you could have. So when you're showing your neutron star perspective, what you can maybe find in neutron stars, I remember that when I was a graduate school, it was kind of interesting. People were talking about color superconductivity.
Yeah.
So what is the status of that? And I mean, what is the experimental perspective for this kind of?
The status is still like this, the way you remember it. That phase of color superconductivity has a very good theoretical basis. And there is even another state called color flavor locked. I don't exactly know what it is. Color superconductivity is like in normal superconductivity. Is pairing two electrons give us the Cooper pairs. You can equally pair two quarks. That would give us the equivalent of the Cooper pair in, in electromagnetism superconductivity. So this is, the analogy there is rather clear. Now the experimental problem is that these phases are predicted to lie at low temperatures. In this regime of the phase diagram, around here, beyond the normal nuclear matter density, so in this regime, and we have no idea, and it may even be impossible ultimately, how to cook such a state in our collisions without heating. So our collisions do not go without heating. And you know, you see, even without, after the cooling, we end up at temperatures which are of the order of 50 MeV or so, while those states are predicted to be below 20 or so, and at this large baryochemical potential. So the prospects experimentally are unfortunately not at the horizon. Okay, maybe a breakthrough idea, but I really don't see how this could be realized. Yeah. Now, if I may add, in the neutron stars, in the center of the neutron stars, those states can exist. Neutron stars are cold objects. We don't have probes of the interior of the neutron stars, but when they collide, maybe we would be able to see via the change in the equation of state, via the modeling of the melting collision in the sense of melting. Of course, they don't collide, but melt together. We may have a chance to see indirectly via the outcome whether there was an exotic state. It's not yet obvious how, but this may be our chance. There is, I think, for the neutron stars, some observations of glitches in their rotation may suggest the presence of superconductivity, but that's also not conclusive.
Yeah, one other such phase I remember, but this one is kind of novel for me because it was like last year I came to know about it. Someone was trying to calculate the idea that you can form bound state, but with a finite momentum. You know, it's like a Cooper pair, but with a finite momentum, which would give you some oscillations in the density.
Yeah.
For, you know, like kind of stuff. So I don't know how. I mean, this is what in condensed matter we kind of call like a charge density wave or something like that. But I think that in the case of would be like it would be really oscillations in density. So,
yeah.
But I guess by your answer that I would also expect this in this odd region in your phase diagram as well, right? I mean, this is not experimentally accessible thing. Or
this is less hopeless, actually,
I see.
because now there are newer insights that in the vicinity of the critical endpoint in this region, also you can produce such type of regimes, of fluctuating regimes, and our theory colleagues are trying to make more quantitative predictions. For the moment, they're a bit more generic. But those regimes of changes in density, fluctuating, and so are expected around this region. This region here, whether there is a critical point beyond which a first-order phase transition would be the case, is debated, and seems to be located in this region, and such fluctuating observables can be visible in this region, can appear in this region of the phase diagram. So that is one of the motivations for the newcomer experiment CBM at FAIR to maybe even detect that.
Thank you.
Thank you.
More questions?
So the natural but I think uncomfortable question that comes after Leonardo's is, do you think that the unexpected result for the Fourier coefficients for PP is enough for contest the idea of using PP collisions as baseline for QGP effects?
No, using proton-proton collisions as a reference when we built ratios from observables in lead-lead, for instance, compared to PP, is still okay as soon as you take so-called minimum bias proton-proton collisions, namely an average of all possible events. Now, the presence of flow is here, you see it here, is for all multiplicity ranges, but the minimum bias case is around here. You know, it's even below the range covered by these points. Okay. They are not so obviously characterized by flow, and even if they are, they can still be a reference. I think this does not introduce a bias. But of course, the high multiplicity events, sorted events of this type, are physics study, physics object on their own, definitely.
On average?
On average, it's still okay. Quite sensible to use proton-proton collisions as reference, as normalization sometimes even. Yeah.
Okay. Thank you.
Thanks for the talk, very nice. I'm not from the area, and I have probably a very naive question. When you have this collision between all this stuff there, you apply the conservation laws of physics.
Yes.
And nothing is missing. Is there any possibility to find something which is not working, to imagine that you are producing dark matter?
Yeah. Yes, to imagine, of course, is all allowed. In fact, our colleagues in particle physics, when colliding protons, have so many more collisions than in case of lead nuclei, that they are more sensitive to exotic particles, like dark matter candidates. And they have imposed limits on masses above about, I think, 1 TeV up to almost 10 TeV. So candidates with that mass are excluded. Well, we don't know what the mass of a dark matter, possible dark matter particle, don't even know if dark matter is a particle or something more strange. Of course, this is all known, but under the assumption that dark matter has a particle nature, a big range was excluded already with higher efficiency and precision by our colleagues in the high energy physics, in the proton-proton collision, particle physics colleagues. In the nuclear collision here, well, of course, the energy densities are larger. You have a larger fireball. The question is whether the QCD vacuum produces something differently. For the moment, we don't have any indication. Of course, we search for particles like the so-called dark photon, which is a candidate for nuclear matter. We have some limits, not very precise still. Of course, we keep doing, but we do this as a bonus, aside. It's not our bread and butter. We are actually quite busy doing what I was showing here, that not so much is left for the other searches, which is a pity. Maybe it could be intensified, because certainly it makes sense to look. But one needs, in addition, a guided look, right? This is, I mean, looking everywhere, you would find nothing, in a sense, right? One needs a guided method, so to say. We don't really have that many of them. Yeah. Thank you.
Thanks for the talk. I'd like you to come back to the plot of the statistical hadronization model. Yeah, it's a beautiful plot. Do you, I wanted to take from this some picture, some clear picture of how particles are produced.
Yeah.
So I understand that what comes from this plot is that you have first a hot phase with quarks, and then it hadronizes, producing the particles, and then there's nothing else.
Yes.
This is what you get, even because of the temperature that you get there to feed the data is almost a transition temperature.
Yes, yes.
So then you would exclude the existence of a hadron gas phase.
No. There could be still rescattering in a hadron gas that do not change the identity of the particles. That will be elastic scattering. So at this moment, when the hadrons are produced, the inelastic collision scatterings cease, stop. And in this model, actually, sudden, immediately, the time, zero time. Of course, there could be a little smearing. There will be with a small effect. But beyond this temperature, for another Fermi over C or 2 or 3, down to a cooling of about 120, so cooling by another 30 MeV or so, you could still have scattering in a dilute hadronic gas that would lead to some change in the momentum of particles. So a redistribution of momenta among particles, but not a change of identities anymore. So on this, we still debate. We don't know well enough the duration of that phase.
Do you know this data about K-star abundances? So to me, it seems that they are indicating that there is still something left, because the K-star has a strong decay and into K plus pi, and you miss them, so you cannot reconstruct.
The products of the decay are scattered later in the hadronic gas. Indeed, via such measurements, we could tell that the hadronic phase had a lifetime of a few Fermi over C, just by convoluting what you miss with the lifetime of a K0, so to say. And indeed, we have indication that there is a hadronic phase. But once again, that hadronic phase does not change the identity of the particles.
It is also amazing that the numbers do not depend on the wave function of the spatial nature of the particle. The deuteron is completely different from the kaon of ion, and still it seems that it doesn't matter. That's quite interesting.
It's in the first order like this. We now start to see, with more precise data, in fact, that we have some deviations from this first order picture. And there is a comment here. We see some discrepancies with the newer data, and it seems the wave function, exactly as you pointed out, via the size of the particle, I mean, expressed in the wave function, coded in the wave function, is playing a role. We don't have a clear picture yet, in fact, whether this is a consistent picture or not. But definitely, there is more than what I am showing here. That's a first order description, I would say. Yeah.
Any other question? No. So let's thank Anton again.
Thank you
very much.